Okay, continuing along. So we're going to take this idea of Gibbs free energy or the chemical potential and look at how its variation with temperature and pressure creates a phase diagram. So we're going to look at one section at a time. So as a reminder, we can now say the partial of chemical potential with respect to the partial of temperature at constant pressure equals negative molar entropy. Thus, a graph of chemical potential versus temperature will yield a straight line with a negative slope, and the slope of that line is the molar entropy. So now we can see we have this plotted for three different phases. And it's worthwhile to note here that the molar entropy of a gas will be greater than the molar entropy of a liquid, which will be greater than the molar entropy of a solid, all quantities being greater than 0. So that's why we see them having negative slopes, and we see the gas has the steepest slope, followed by the liquid, followed by the solid. So that is all good. So if we play with this idea of dG being this partial molar quantity, we can look at how Gibbs changes from some initial state to some final state. Okay, and that's going to be given as mu2, or I'll use final minus initial so it's less confusing. So that would be mu final minus mu initial, and then we have to multiply that by the change in number of moles to make all these units work out, right? Remember, Gm equals mu over n. So of course, if we multiply both sides by n, we can see we just have G. So now, if mu initial, if the chemical potential initially is greater than the chemical potential in the final state, then what that means is dG will be less than 0. And thus, if we go from some initial phase to some final phase and the free energy change is negative, then it will spontaneously undergo that phase transition. Okay? If mu initial equals mu final, then dG equals 0, and those two phases are in equilibrium with each other, okay? Which would represent a critical point on our phase diagram. So now if we take a look at this here, okay, what we should start kind of accepting now with chemical potential, the lowest chemical potential of a given temperature is going to be the one that is observed in nature. So if I start all the way here at the lowest temperature that I can get to, my lowest chemical potential is a solid. So the solid phase will be observed all the way up until I get to this point right there. So now at this point, we can see here the chemical potential of the liquid and the chemical potential of the solid are equal. So those two phases will be in equilibrium with each other. And something very special happens at that point. That is called the melting point or the fusion point, okay? And so now if we move past this point, the liquid has the lowest chemical potential. And so that is the one that's going to be observed, okay? So now we've passed the fusion point and we're on this liquid line. We hit this other point where the two chemical potentials are intersecting, right? And we can see that's an intersection of the liquid and the gas. So that is what we call T vape or T boiling. And so once we've gotten past that point now, our gas has the lowest chemical potential, so it is the phase that will be observed, right? Okay, beautiful. And so you can imagine now if we go the other way, if we start at a high temperature and move our way back, it will be the same scenario. Starting at a high temperature, the gas is the lowest chemical potential. We'll cross that line, then the liquid has the lowest chemical potential. We'll cross that line again, then the solid has the lowest chemical potential. It's also worth noting here, we can see the presence of a sublimation point right there, T sub, where a solid and gas are in equilibrium. However, in this particular graph, we can see that sublimation point does not minimize relative to the fusion or the vaporization. So under these conditions, a sublimation would not be observed. However, we can imagine now changing pressure might result in that sublimation point having the lowest chemical potential, and thus that would be the observed phase. Okay, so let's look at the other dimension, which is related to changes in pressure. So we can say the partial of mu with respect to the partial of P at constant T equals Vm. And it's now we can start to see here that there's some curvature to these lines. So the liquid and the solid have a nice steady slope equal to positive Vm, but now there's a little bit of curvature going on. And that's because the volume of a gas is not static, rather the volume of a gas changes in accordance to the ideal gas law or even the van der Waals equation. So that's why we see some curvature. And so now we can play the same game. The molar volume of a gas, as it turns out, is much, much greater than the molar volume of a liquid, which is greater than the molar volume of a solid. So this is the case with most materials except H2O, a notable exception. So H2O, the molar volume of the solid, is actually bigger than the molar volume of the liquid, right? So if I look at those values for H2O gas, right, we'll assume ideal behavior, so that's 22.42 liters per mole. The molar volume of water as a liquid is 1 over the density expressed in units of liters per mole. So that is 0.0180 liters over moles, and that comes from 1 gram per milliliter. So that number is the same as 1 gram per milliliter, the bulk density of water. So obviously we had to do some unit conversion to get those, okay? But then this is the interesting case for water, right? The molar volume of water as a solid is larger than its molar volume as a liquid. Or in other words, what's really going on here is because the density of the solid is less than that of the liquid. So the density of ice is about 0.9 grams per milliliter, which remember is the opposite of like basically everything. So this is the case with almost all materials. The molar volume of the gas is much, much greater than the molar volume of the liquid, which is greater than the molar volume of the solid. However, water is our one exception now, where the molar volume of the solid is greater than the molar volume of the liquid, because the density of solid water or ice is less than the density of the liquid, right? Your ice cube floats on top of your beverage, okay? So now we have to figure out how we can get this relationship to describe this gas phase line. So we're going to integrate an expression from initial to final. We're going to integrate dGm at constant t, right? Because that's what this relationship is. And so that is going to become Vm dP, right? So I just moved those two things over to the other side. And we know that Vm for an ideal gas is equal to RT over P dP, right? Because Vm equals RT over P. Sorry, I wrote that twice. Or in other words, V equals RT over NP. So PV, did I get that right? Oops, I have to divide the number of moles on the other side, right? So in other words, V over N equals RT over P, right? Because we're doing the molar volume. So now if I integrate this expression, I'm going to end up with the following. So integrate the dG, and that's going to be Gm at some final pressure equals Gm at some initial pressure. So we know this will be final minus initial. So then I just add it over to the other side. And then now plus the result of this integral, which will become RT times the natural log of P final over P initial. And of course, using chemical potentials, the way that we will often see this expression written more commonly will be mu final equals mu initial plus RT natural log of P final over P initial. And that's actually what this curve is right here, okay? So now we have to combine these two axes in order to make a phase diagram. And we have to remember the phase that has the lowest overall chemical potential is the one that will be observed. So we can make this like rather fantastic looking 3D diagram where now each one of those surfaces, like I showed you in the first video, corresponds to any one pure phase. So here I've indicated the red is the gas phase, the blue is the liquid phase, and the green is the solid phase. So again, right, I'll go back up to that top slide so we know where this is coming from. So I showed you this in that first video, right? This is the surface of any one pure phase. So now to make a phase diagram, we've got all three of those surfaces superimposed. And once again, the phase with the lowest chemical potential is the one that's observed. So to go from this three-dimensional graph to what we more traditionally see here in this phase diagram, we have to flip this thing upside down and look at the minimas. And then lo and behold, here we have a rendering of this 3D phase diagram into this 2D phase diagram. And of course, I did this for H2O. And we can see right here, there's the triple point predicted to be at 273.16 and 0.006 ATM. We can see there the boundary between the liquid and the gas phase line and the boundary between the liquid and the solid line. And those occur where those chemical potentials cross each other and then minimize. Okay, so we'll play around with these kind of like 3D graphs in more detail in our live lecture. I'll see you in the next video.